Hello, discrete math fans. Let's talk about graphs. Graphs are one of the most important structures in mathematics, which leads them to being one of the most important data structures in computer science. This is an example of a graph. It may be useful for you to draw this picture because we're going to refer to it a few times as we go along. Now, this is very different from the type of graph that you learned in algebra and pre-calculus. In the picture, the circles are called vertices, and the lines connecting the vertices are called edges. Edges can cross at points that are not vertices. That will not create new vertices. It's worth pointing out that you can have an edge that connects a vertex to itself. Notice that in the picture, there's an edge that goes from A back to A. We're going to call such an edge a loop. Notice also that there are two different edges that go from C to D. We're going to call those parallel edges. We're not using parallel in the geometric sense. The concept of a graph is not a geometric thing. In fact, it is what we'll call a topological concept. So whether we draw the edges curved or straight or some other way, that's irrelevant. What matters is what the edges are connecting, which vertices. Now sometimes a vertex has no connection to other vertices. So back in our picture, that would be vertex G. That vertex is called isolated. And of course, we'll want to label our vertices and edges for further discussion. So this graph has vertex set A, B, C, D, E, F, G, and has edge set E1 through E7. We're going to say, for example, that edge E3 is incident on A and E, and thus A and E are adjacent. We're also going to say that the endpoints of E3 are A and E. So there's just some language that we need to get used to. The correspondence from edges to endpoints is called the edge-endpoint function. All right, so as an example, let's write down the edge-endpoint function of the graph that we've been talking about. And it just looks like this. So we take each edge and map it to the set of endpoints that it is an incident on. So what we should see in here is that E4 is connecting C and D. E1, remember, was a loop. It connects A and A. All right, just so that we have it, let's give a complete and formal definition of a graph. We've discussed most of the terms that we'll talk about here, but not all of them. So a graph G consists of two finite sets, a non-empty set V of vertices and a set E of edges, where each edge is associated with a set consisting of either one or two vertices, called its endpoints. The correspondence from edges to endpoints is called the edge-endpoint function. Continuing with our definition, we'll just say that an edge with just one endpoint is called a loop. Two or more distinct edges with the same set of endpoints are called parallel. An edge is said to connect its two endpoints. Two vertices that are connected by an edge are called adjacent, and a vertex that is the endpoint of a loop is said to be adjacent to itself. And an edge is said to be incident on each of its endpoints, and two edges incident on the same endpoint are called adjacent. And finally, a vertex on which no edges are incident is called isolated. Now, there's a lot of different language here. I don't think you need to memorize all this, but they will naturally come up in the course of talking about graphs. You may need to refer back to this list of definitions that we've talked about. Okay, that's all for now.